Hey guys, I am going to give the solution of assignment 4. So now in problem second, we need to find the pole and its order and also find its residue at each pole. So in this problem, let us consider the given function f of z, that is z square over z negative 1 to whole square multiplied to z plus 2. First of all, we need to put the denominator z negative 1 to whole square z plus 2 is equal to 0 to find singularity. It implies value of z is equal to 1 comma negative 2. It implies value of z is equal to 1 comma negative 2 are singular point, or we can say that is a singular points. So now we need to check the nature of this singular point. As we can see in denominator, factor of z negative 1 is 2 and factor of z plus 2 is a 1. So we need to find the nature of this singular point. So we can say that value of z is equal to 1 and negative 2 are poles, because as z tending to 1, f of z tending to infinity, and as z tending to negative 2, f of z tending to again infinity, it shows that the singular point z is equal to 1 and negative 2 are the poles. So now further we need to find its order. So now the limit z tending to 1, z negative 1 to the power m multiplied to f of z, this is equal to the limit z tending to 1, z negative 1 to the power m, and the f of z, that is z square over z negative 1 to whole square z plus 2, that is limit z tending to 1, z negative 1 to the whole power m negative 2 z square over z plus 2. So the value of this limit will be, if I take the value of m greater than 2, limit will be 0. If I take the value of m is equal to 2, then this factor will be vanishes. And put the limit here, it will give 1 by 3, which is non-zero quantity. And if I take the m less than 2, it will give infinity. So we can say the limit z tending to 1, z negative 1 to the power m, f of z is equal to 1 by 3 4 m is equal to 2. So therefore z is equal to 1 is a pole of order 2. Similarly, we need to check the order of pole, that is the limit z tending to negative 2, z negative of negative 2 f of z, the whole power m, that is the limit z tending to negative 2, z plus 2 to the whole power m, z square over z negative 1 to whole square z plus 2, that is the limit z tending to negative 2, z plus 2 to the whole power m negative 1, z square over, that is we can write z negative 1 to whole square, and the value of this limit, if I take m greater than 1, its limit will be 0. If I take m is equal to 1, then its limit will be, that is a 4 upon that is 9, which is non-zero. And if I take m less than 1, that is infinity. So we can it implies that limit z tending to -2, z plus 2 to the whole power m f of z is equal to 4 by 9, that is non-zero quantity 4, m is equal to 1. So therefore we can say z is equal to -2 is a pole of order 1, or we can say that is a simple pole. So now further we need to find the residue of each pole. So now the residue at z is equal to 1, that is the limit z tending to 1, 1 upon 2 negative 1 factorial d over dz of z negative 1 to the whole square f of z, that is z square, over z negative 1 to whole square multiply to z plus 2. So we can say this factor get cancel out. So now further we need to find the derivative. So that is its derivative will be, that is z plus 2 on derivative of z square, that 2 times of z negative z square, derivative of z plus 2, that is of 1 over z plus 2 to the whole square. So now direct we can substitute the limit here. So we will get 1 plus 2, that is a 3, multiply 2 negative 1 over 3 square, that is a 9. So that is 5 over 9. So we can write here the value of the residue at z is equal to 1 is equal to 5 over 9, and this is our required answer. Similarly, we can find the residue for the simple pole z is equal to -2. So by the formula we can write z tending to -2 for the simple pole, that is z plus 2 f of z, that is z square over z negative 1 to whole square z plus 2. We can say this factor get cancel out. So now further this value is equal to, we can put direct the limit here, that is -2 to whole square over -2 -1 whole square, that is 4 over 9. So therefore the value of the residue at z is equal to -2 is equal to 4 over 9, and this is our required answer. So now in this problem we need to find the residue of the function f at its pole. So first of all we need to put z negative a to the whole power 3 is equal to 0. It implies value of z is equal to a. So we can say z is equal to a is a pole because z tending to a, f of z tending to infinity. So now we need to find the order. So by definition, limit z tending to a, z negative a to the whole power m, f of z, that is limit z tending to a, z negative a to the whole power m, f of z, z e to the power of z over z negative a to the whole power 3. So we can write here the limit z tending to a, z negative a to the whole power m negative 3, z e to the power of z. This limit will be, that is if I take the m greater than 3, this limit will be 0. If I take m is equal to 3, this limit will be, so this factor will be vanishes. So we can write here, that is a e to the power of a, which is non-zero quantity. And if I take m less than 3, limit will be infinity. So we can write here, the limit z tending to a, z negative a to whole power 3, sorry, whole power m, f of z is equal to a e to the power of a, which is non-zero quantity, for m is equal to 3. So we can write z is equal to a is a pole of order 3. So now we can find the residue of this given complex wave function easily by using the formula. So that is residue at z is equal to a will be the limit z tending to a 1 upon 3 negative 1 factorial second derivative over dz square z negative a to the whole power 3 z e to the power of z over z negative a whole power 3. So here this factor get cancelled out. So now we need to find the first derivative. It will give 1 upon 2 factorial limit z tending to a, and the first find the first derivative with respect to z. It will give e to the power of z plus z e to the power of z, and again differentiate, we will get 1 by 2 z tending to a e to the power of z plus e to the power of z plus z e to the power of z. So put the limit here, 1 by 2, that is e to the power of a plus e to the power of a plus a e to the power of a. So as we can see, this is equal to 1 by 2, 2 times of e to the power of a plus a e to the power of a. So take e to the power of a as a common, and it will give 1 by 2 e to the power of a by 2 a plus 2. So it implies the value of the residue at z is equal to a is this, and this is a very quite final answer. So now in the first a, in the problem 4, in first a part, we need to put the denominator z negative a, z negative b, z negative c is equal to 0. We will get value of z, that is a comma b comma c. So as z tending to a, f of z tending to infinity, as z tending to b, f of z tending to infinity, and as z tending to c, f of z tending to infinity. So we can imply that z is equal to a comma b comma c are poles of the complex value function f of z. So now the limit z tending to a, z negative a of the function z square over z negative a, z negative b, and z negative c. So we can see here this factor get cancel out, or we can find the limit, that is a square over a negative b and a negative c, which is non-zero. So it implies value of z is equal to a is a simple poles. Similarly, we can find the limit z tending to p, z negative p, z square over z negative a, z negative b, z negative c. That is, this factor get cancelled out. So this value is equal to, that is, b square over b negative a, b negative c, which is non-zero. It implies value of z is equal to b is a simple pole. Similarly, we can find the limit z tending to c, z negative c, z square over z negative a, z negative b, z negative c. So this factor get cancelled out, and the value of this limit, that is c square over c negative a, c negative b, which is non-zero. It implies z is equal to c is a simple pole. And for simple pole, order of order order of the singularity is 1, or order of pole is 1. So we can write z is equal to a comma b comma c are the poles of order 1. So this is a very quiet answer. Now in part B, the given function f of z, z e to the power of I times of z over z square plus a square. We need to put z square plus a square is equal to 0. It implies value of z is equal to plus minus a, plus minus ai, and as z tending to ai, f of z tending to infinity, and as z tending to negative ai, f of z tending to infinity, it implies the singularity z is equal to plus minus ai are poles. So now we need to find the order of this pole. So first we need to find limit z tending to ai, that is z negative ai, f of z, z e to the power of iz over z square plus a square. We can find the limit z tending to ai, z negative ai, that is z e to the power of I times of z over z plus ai, z negative ai. So this factor get cancelled out, and put the limit here, that is a I e to the power of negative a over 2 ai. So we can see here ai get cancelled out. So this value is equal to e to the power of negative a over 2, which is non-zero. So we can write here value of z is equal to ai is a simple pole. Similarly, we can find the limit z tending to negative ai, z plus ai, z e to the power of iz over z square plus a square. There is a limit z tending to negative ai, z plus ai, z e to the power of iz over z plus ai multiplied to z negative ai. So here this factor get cancelled out. Put the limit here. You will get negative ai e to the power of a over negative 2ai, you can see negative negative get cancel out, ai get cancel out, and this value is equal to e to the power of a over 2, which is non-zero. So it shows that z is equal to negative I is a simple pole. So therefore z is equal to ai and negative ai are poles of order 1. So this is our required final answer. So now in part C, the given function f of z, z negative 3 over z negative 2 to whole square multiplied to z plus 1. So first of all we need to put the denominator z negative 2 to the whole square multiplied to z plus 1 is equal to 0. It implies value of z is equal to negative 1 and 2. So as z tending to 2, f of z will tending to infinity, and as z tending to negative 1, given f of z tending to infinity, it implies value of z, that is negative 1 and 2, are poles of the complex value function f of z. Now we need to find the order of this pole. So first of all we need to find the limit z tending to negative 1, z plus 1 to the whole power m, f of z, z negative 3 over z negative 2 to the whole square, z plus 1. So this limit will be, if I take m greater than 1, this limit will be 0. If I take m is equal to 1, this limit will be, we can say the factor will be cancelled out. We can put the limit directly, that is a negative 4 over 9, which is non-zero quantity. And if I take the m less than 1, obviously this limit will be infinity. So from here we can imply that the singularity z is equal to negative 1, that is a pole, is a simple pole. Simple pole, that means z is equal to negative 1 is a pole of order 1. So this is our answer. Similarly, we can find the order of the pole at 2, that is z negative 2 to the power m, f of z, z negative 3 over z negative 2 to the whole power 2, z plus 1. This limit will be, if I take z is equal to 2, then limit will be, that is negative 1 upon 3, which is non-zero quantity. If I take the z less than 2, that is infinity. If I take z greater than 2, that is a 0. So we can say that z is equal to 2 is a pole of order 2, because for this m is equal to 2, limit is non-zero. So this is our required answer. So now in problem 5, we need to find the residue of all complex value function at the given singularity. So in problem first, the f of z can be written as, we can use the Taylor series or Laurent series expansion of the given function. The Laurent series expansion of the sin 1 by z will be, that is 1 by z negative 1 by 3 factorial z to the power 3 plus 1 upon 5 factorial z to the power 5 negative dot dot dot. So now multiply by z square. So we can see it will give z negative 1 by 3 factorial multiplied to z plus 1 upon 5 factorial z to the power 3 negative dot dot dot. So as we can see that the residue at z is equal to 0 will be the coefficient of 1 by z in Laurent series expansion of the function f of z at z is equal to 0. So the coefficient is, we can see the term this one. So this is our required coefficient of 1 by z in the Laurent series expansion. So this value is equal to negative 1 upon 3 factorial, that is negative 1 upon 6. We can write here the value of residue at z is equal to 0 is equal to negative 1 by 6. So this is our required answer. So now in problem B, the given function f of z, that is 1 plus e to the power of z over sin z plus z cos of z. So we need to find the residue at z is equal to 0. So now here we can express the function f of z, that is phi of z over psi of z. So now here phi of z, by comparing we will get 1 plus e to the power of z, and psi of z is equal to sin z plus z cos of z. So here at a point phi psi of 0 is equal to 2, which is non-zero, but psi of 0, it will give 0 plus 0, that become a 0. Now differentiate the differentiate the psi with respect to z. So it will give cos of z, that is a plus cos of z, negative z sin z. So it implies psi dash of 0 is equal to 2, which is non-zero. So we can write here z is equal to 0 is a simple pole, is a simple pole. That is very important. If this is a simple pole, so the value of the residue at z is equal to 0 is equal to phi of 0 over psi dash of 0. So phi of 0, that is a 2, and psi dash of 0, that is a 2. 2 to get cancel out, and this value is equal to 1. So the value of the residue at z is equal to 0 is equal to 1, and this is our required answer. In problem third, the given complex value function f of z 1 upon z multiplied to e to the power of z negative 1. So we need to find the residue at 0 and z is equal to 2n pi separately, 2n pi I. So first of all we need to put the denominator z e to the power of z negative 1 is equal to 0. So from here value of get is equal to 0 and e to the power of z is equal to 1. So e to the power of z is equal to 1, that is we can write the 1 e to the power of 2n pi I. So from here value of z is equal to 2n pi I, where n belongs to all set of integer z. So that is z is equal to 0 and 2n pi I are singular points. Further, we need to find the residue. We need to find the residue at z is equal to 0. So at z is equal to 0, we need to calculate. So first we can find the function f of z is 1 upon z e to the power of z negative 1. So that is by using the Taylor series expansion of z, that is 1 plus z square over 2 factorial plus z to the power of 3 over 3 factorial plus dot 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 negative 1. 1 negative 1 get cancel out. Take the z as a common, that is z square 1 plus z by 2 factorial plus z square by 3 factorial plus dot dot dot. So now here we can write here that it's 1 upon z square, that is 1 plus z by 2 factorial plus z square by 3 factorial plus dot 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 whole inverse. So let us suppose this is as a x, and as we know that 1 plus x whole inverse is equal to 1 negative x plus x square negative x to the power 3 plus dot dot dot. So by using this series we can express above 1 by z square, that is 1 negative z by 2 factorial plus z square by 3 factorial plus dot 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 and plus z by 2 factorial plus z square by 3 factorial plus dot 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 whole square negative dot dot dot, and now divide the whole bracket by z square. It will give 1 by z square. It will give, that is 1 by 2 factorial multiplied to z, that is 1 by 3 factorial plus dot dot dot. And if I take the z square, if I take the z as a common from this whole square, then z square will vanishes and it will give 1 by 2 factorial plus z by 3 factorial plus dot 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 to whole square negative dot 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 this. So now the residue at z is equal to 0, that is the coefficient of 1 by z in Laurent series expansion of the function f of z at z is equal to 0. So this is our required value. So from here, that is negative 1 by 2 factorial, that is negative 1 by 2. So therefore the value of residue at z is equal to 0 is equal to negative 1 by 2. So this is our required answer. So now further we need to find the residue at z is equal to 2 n pi I. So first of all, we need to consider f of z, that is 1 upon z e to the power of z negative 1. So we can write here that is 1 by z upon e to the power of z negative 1. So by comparing with phi of z upon psi of z, here phi of z is equal to 1 by z and the psi of z is equal to e to the power of z negative 1. Here phi of 2n pi I, that is 1 upon 2n pi I, that is a non-zero for all n belongs to z at except 0, because we have already calculated at z is equal to 0. Now further, psi of 2n pi I, it will give e to the power of 2n pi I negative 1, that is 1 negative 1 is equal to 0. So now we need to find the derivative. Differentiate this psi with respect to z. It will give e to the power of z. It implies value of psi, derivative psi at 2n pi I. It will give 1, which is non-zero. So therefore, the residue at z is equal to 2n pi I, it will give phi of 2n pi I over derivative of psi at 2n pi I. So this will give 1 upon 2n pi I upon 1. So this value is equal to 1 upon 2n pi I. 1 by I, for 1 by I we can write negative I by 2n pi. So our final answer will be, that is the value of residue at z is equal to 2n pi I is equal to 1 of negative I upon 2n pi, where n belongs to set of integer except 0. So this is our required final answer.